Hello everyone, welcome back to the channel. So today we'll be diving into one of the most powerful ideation in deep learning, that is convolutional neural networks (CNN). By the end of this video, you'll understand that how it works, how they are being built, and what is the architecture like the ResNet changed everything. Okay, so starting we start that what even is CNN. A convolution neural network is a deep learning architecture that's specifically built for a data that has spatial structure. Imagine you have a video or the audio spectrogram. Okay, now here's the core insight about the CNN. A cat is in the top left corner of an image is the same cat as the bottom right corner. The feature is same, just at different location. CNN exploit this using something called as the translation invariance. The same filter scan the entire image to detect feature no matter where it appears. You might ask that why not just use a regular fully connected neural network? Here's a problem. A 224 cross 224 RGB image has roughly 150k inputs. A fully connected layer would need hundred of millions of parameters just for one layer. It would flatten the image, destroying all the spatial information, and it would need to relearn the same feature at every single position. That's massively inefficient. CNN fixed this all: tiny parameter count, spatial structure preserved, and feature detection anywhere in the image. Alright, let's talk about the heart of CNN, the convolution operation. The idea is simple, that it's a small filter, say 3 cross 3, and slide it across your input image. At every position, your compute dot product between the filter and the patches of the image. The result cap writes out the feature called as a feature map. Mathematically, for a 2D input, a kernel, k cross k output, the output at a position I cross j is the sum of the element-wise product of the kernel with the respond of the input patches plus a bias term that it is. Okay. Now the output size after the convolution is being given as floor of w minus f plus 2p by s plus 1, where w is the input width, f is the filter size, p is the padding, and s is the stride. Now taking a quick example of 6 cross 6 input, 3 cross 3 filter, no padding, stride equals to 1, output is going to be 4 cross 4. Okay. Now for the key feature about the hyperparameter, filter size f. Okay, so typically 3 cross 3, first layer sometimes uses 7 cross 7. Now the number of filters that will control the depth of the output, typically double of every block. For example, 32 to 64 to 128, unlike this. Okay, then we have stride. Step size of the filter, stride 2 for the spatial dimensions, and padding p, same padding preserve size, valid means no padding. Okay, now this concept of the pooling layer. After convolution, we also apply pooling to downsample the feature map. The most common is the max pooling. You slide a 2 cross 2 window with a stride of 2, just taking the maximum value in each row, and then the half between the spatial dimension while keeping the strongest activation. Now you have an average pooling where you take the mean and smoother, use it in the later layer, and a global average pooling which collapse an entire feature map to a single number. Greater replacement for the flattened layer before classification. Modern network like the ResNet actually skips pooling entirely and just use stride convolution to downsample. Okay, now we'll go through the full CNN architecture. So the question comes that how does a full CNN architecture look? You start with the input image, the alternate block of convolution, a batch normalization, ReLU, and pooling. This is repeated several times. Now going depth and narrow, spartily but reaching the channel. Now you get a flatten, use globally average pooling, passes through fully connected layer, and output class scores through a softmax. The magic is in the feature hierarchy this build. Early layers detect edges and color, middle layer detect the texture and shape, deep layer detects the object part, and the high level segmentation. Let's talk about parameters. This is where CNN really shines. A convolution has a f squares cross c in plus 1 cross c out parameters. Example is also given: 3 cross 3, 32 input channels, 64 output channels, and about 18,752 parameters. Compute them fully connected layer doing the same thing. You'll be able at millions. That's the power of some weight sharing. Pooling layer have a zero learnable parameter. Batch normalization has just two parameters per channel, gamma and beta. Most of your parameter actually live in a full connected layer at the end. Okay, now the famous architectures are LeanNet 5, okay, the OG one, the first practical CNN for the handwritten digit recognition. Then LXNet, we have VGGNet, GoogleNet, RestNet, MobileNet, EfficientNet. One of the last three are very important for you to know. One is the RestNet, that is the biggest leap, introducing the skip connection, enabling networks with the 100 plus layers. Then we have the mobile net. It is used for mobile and the edge devices separation convolution, and the efficient net that can scale depth, width, and resolution together. Okay. Now, moving forward towards the residual connection, let us spend some time on the ResNet because it's important. So, as network get depth with the time, two problems shows up. One is the vanishing gradient and the degradation. When adding more layers actually make accuracy worse. ResNet fills it elegantly. It add a skip connection, the bypass one or two layer, and add the input directly to the output. So instead of learning a full map, the network only learns the residue, and the output become ReLU fx plus x. Learning a small residue is much less than to optimize. Gradient can flow freely back through the skip path. This is what called as ResNet and ResNet 101 and ResNet 152. All that work brilliantly. Now the regularization part. So before we quickly wrap up, we have something important about the regularization, that is dropout applied after the FC layer randomly zero out the activation during the training. Then we have the batch normalization, that after every convolution layer, it stabilizes the training and reduce the internal covariance shift. Always use it. Then we have data augmentation. This is what we have covered just a video before because it's very important for this. So random cropping, flipping, rotating, zittering, artificially expanding your dataset without collecting new data. That's a huge impact on this. Then we have the weight decay, panelizing large weights, reducing overfitting. And lastly, we have early stop. Monitor the validation loss and stop when it start rising. Okay, here are some of the key takeaways, that CNN use local connectivity and weight sharing. The same filter scans the entire image. Convolution slides a learnable filter across inputs and produces a feature map. Then we have output size floor of W minus F plus 2P up by S plus 1, which memorizes this. Then we have pooling that reduce the spartial size. Modern network prefers stride convolution instead. CNN build a feature hierarchy, edge, text, shape, and objects. ResNet skip connection, solving vanishing gradient and unlock very deep networks. Then lastly, we also have always pair convolution layer with a batch norm plus ReLU, that always use data augmentation. And lastly, for edge deployment, mobile net plus efficient net for better accuracy, ResNet or the efficient net v2. And that's all about the CNN in a nutshell time. From the basic convolution operation to all the way to the ResNet and the modern architectures, we have discussed about like the mobile net and the efficient net. And we'll be covering more of this in coming lectures also. Okay, so thank you from my side.